Alright, so in this video, I'm going to go through essentially how to engineer a suspension structure versus just kind of connecting the hard points with metal tubes and plates and calling it good because it's lighter. When you're trying to build a race car, specifically one that goes around corners, it has to stop very aggressively, consistently. Stiffness and fatigue matter a lot more than just where are the hard points. Because in drag racing, in the front suspension, there's not a whole lot of load that goes into it. There is some when braking, but you're not braking super hard at the end. And so what I see or have seen is a lot of shops build these racing subframes, cradles, whatever, and it's just kind of hard points connected with tubes. And from someone who spent 10 years in vehicle dynamics and coming up on 4 years in the manufacturing side of suspension structures, I kind of look at a lot of that stuff and it looks like it's made out of noodles to me. Um, and so I had a customer, Cory Wells, say, hey, we came up with this cradle. I want you to look at it. I looked at it, said, if you're going to be pulling 2.5, 3Gs around a road course, it's going to need a little more structure to it. And so I kind of walked through how we go from his original design that his fabricator put together to this design that I kind of ended up with, and the justification for why it is the shape it is and why it weighs as much as it does. Because it's really hard to take an OEM stamped steel structure and make it lighter and maintain stiffness or increase stiffness, or to maintain slash increase stiffness and make it lighter. Those it's a stamped steel is a very efficient process, and so I just kind of walked through the how to engineer it, how to get the loads, how to consider the packaging space, how to analyze the suspension, kind of the drawing structure for ensuring that if you have to make a change early on, that your entire model doesn't fall apart later. So that's reducing dimensions as much as possible, so it's all robust. I don't go into a whole lot of detail on any specific aspect. It's kind of a general engineering overview. So if you're interested, have a watch and please give me feedback on how I can improve on the next video, or if there's anything you really want me to go into detail in. So let's just jump into it. Okay, we're gonna try this again. I have not had luck with this, so we're gonna make it quick and dirty because I gotta get it done. So Cory Wells, if you don't know him, he's got some global class records in his front wheel drive Prelude. It's like 650 wheel, 315s, and he's up in his game and making a very serious car, and had a fabricator make a subframe for him, as you can see here. And he's like, hey John, can you look at this and give me some feedback? I'll pay you for it, I know you're busy. And I took one look at it and was like, well, it looks like a pretty typical Honda design or Honda racing subframe that you might find on the internet. But as someone with 10 years of vehicle dynamics experience doing OEM suspension tuning, and now 3.5 years at a manufacturer making welded steel suspension structures for OEMs, I have a pretty good idea of the loads going into suspension, the the direction, the reaction, the magnitude of the loads going in, and then also how to manufacture and fabricate specifically steel welded structures. So I'm a pretty good source for that. 10 years running around the track, changing parts, building calculators, doing math so that you can figure out why stuff's happening and all that good stuff. And so yeah, I looked at this and I was like, maybe for a drag car, bud, but for a car that is hitting 2.5, maybe 3Gs on the racetrack, this isn't going to cut it. And the reason that's so obvious to me is when you look at the OEM Cradle, this guy, there is a lot of boxed structure. All of this stuff is boxed in, right? You've got all these flanges, which add stiffness. I mean, if I don't know how a cross section is going to look, but you know, for reference. So, you know, this is, you know, thickness through here. This is two sheets stuck to each other. This is boxed in down here. This is all boxed in here. And then this is a big flat sheet. As we go further back, you can see that this entire thing, like, this is all boxed in right here, this U channel. It's a big stiff U channel. And not only that, you know, this is bridged here, it's bridged here, it's bridged here. So it's a pretty solid structure. And the reason for that is when someone goes to design really anything on a car, you've got, when it's, you know, a suspension structure, anything like that, you've got, oh, I'm sorry, loads going into the system that are defined in some way. Whether they're accurate or not is a whole nother thing. The more time you spend, the more accurate they are. And then packaging space is the other one. Like, how much space can this take up? Where can it go? Under use, it doesn't hit anything, so you want to make sure your tie rods and your suspension links and your powertrain clears it under dynamic motion. But you also have to account for, you know, manufacturing tolerances. So, you know, ensuring you have a 10 mil gap everywhere is a good idea. But here's the cool thing about steel structures that I've actually came to appreciate significantly since working as a supplier at my company. I used to look at aluminum and be like, yeah, that's the way to go. But from an engineering standpoint, it's like legitimately rare that aluminum makes sense. Steel is so efficient. You know, you look at the weight versus stiffness and strength trade-off you get between steel and aluminum, and while aluminum is a third as stiff, it's a third as light, so you kind of have to use the same mass to accomplish the same things. Now, there's a tons of caveats to that. I'm speaking in generalities here, but fatigue strength of steel is significantly higher than aluminum. So if you have two structures where the aluminum one weighs about as much as the steel one, its fatigue strength isn't going to be that greater. The only advantage it has working for itself is because it is thicker, there is design, like mechanical efficiency to the bending stiffness, bending strength. And so when you take, with stamped steel, this is why it's cool, is you can form it basically into any shape you want, and you can push this material to the furthest outside area of the packaging space. And the reason you want to do that is for stiffness. So this guy, for example, when you look at, I don't remember what it's called. This goes back to like undergrad since the last time I used the term, but there's like a neutral line where the shear or the bending stress is zero if it's just in pure bending, because the top side is going to be in compression and the bottom side is going to be, well, top is in compression, bottom's in tension. So there's going to be a neutral axis in here where there's no force. So yeah, you can bend it this much, but if I turn it, it hasn't changed dimensions, it hasn't changed geometry, it hasn't changed mass, it hasn't changed anything. But now if I try to bend it, it doesn't want to go anywhere. And that's because in this orientation, you have the same amount of material, but it's further from the neutral axis, which means that you get a higher resistance to bending. So that is a caveat with aluminum. I'm not going to say steel is always better, whatever, but for the most part, it does pretty good, especially when you actually do the fatigue analysis and realize that fatigue is generally the limiting factor with most cases. Race cars, it's arguable, because if it breaks, you replace it. You know, the best race car falls apart as soon as it crosses the finish line, whatever. But in the real world, I'm not going to design something unless I have, you know, $50K in software and significant testing and validation tools available. I'm not going to design something that has a life. Anything I sell to a customer under my name or with my business logo on it is going to be designed for a street car to last the life of the car, just like the OEM intended for a lot of these steel structures. And so when I look at this cradle that he made, I'm like, man, okay, sure, it's lighter, but even if you made a tube frame cradle that matches the weight of the OEM one, you're basically moving your material to the neutral line, where the forces pass through. And so you're not really giving yourself any bending stiffness when you do that. So if your goal is to replicate, the only reason you're going to do this is because you have a race car and you're like, I want it to be better. So it could be lighter, maybe. There's a You're going to have a hard time making it stiffer than the OEM part if it's lighter. Or you can make it stiffer, which means it's going to be heavier than the OEM part, because you're not using the same technology. You're not using as efficient design. Tubes and sheet, like flat sheet, great for aftermarket fabrication. It's easy to work with, but it's just super inefficient. Look at all this metal down here and up here. That's all resisting bending, right? So yeah, I looked at this and I'm like, for a drag car that's not going to be experiencing like really any forces in the cradle other than maybe the transmission mount, sure, but 2.5, 3 Gs, you're going to go around a corner and your stuff's going to fall apart. And he's like, huh, okay, well, can I pay you to run through it and give some advice? And so that's where we started. And so I ended up with this cradle, and I looked at it and I was like, huh, where'd you get the CAD for this? Because, okay, come on. Because none of it really looks symmetrical. This surface doesn't match that surface. This surface is well below this surface. And I suspected this was based on a 3D scan that just wasn't done well. Or his car is super twisted. The thing about 3D scanners is it's about like ChatGPT. Yeah, sure, you can wave it around and it will record data and give you a picture, but it doesn't mean it's accurate. I had a really low quality scanner that I started using when I started the business, and I found quickly that it can lose its point of reference, but kind of stitch things together to make it look right, even though it isn't. And so he said, "No, this is an accurate scan. We scanned the car," and I said, "Okay, well, if your plan is to sell this, it might be a good idea to match OEM hard points." And I know for a fact that they're not that shape because 3 years ago, before I started the business and I started working on my race car, I had baselined, or I had put into CAD all the kinematics of the CB Accord and the BB6 SH Prelude to compare the kinematics, because I plan on using the Prelude, a lot of the stuff from the Prelude SH in my car. And so I already had a full kinematic model of the car, and lo and behold, would you look at it, they don't match up. So I said, okay, here's the deal. We can assume that this 3D scan, by the way, is mine. I do think he provided one. I did not end up importing it, I don't think. But let's assume that this cradle is correct to your car. I might suggest straightening your car out, but since you're going to resell it, we need to make it straight. And so step one, I needed a good baseline. Now, I wasn't going to redesign this entire OEM cradle to figure out how stiff and how strong it is. That was going to be a lot of work, and he needed results pretty quick. But what I do know is his car, about what it weighs, and what he plans on doing with it. And the rest is just kind of engineering. And so here's where we started, as I said, all right, well, let's figure out the loads. To figure out the loads, we need to know from the tire patch, if there's a load on the tire patch, what does that load translate to in the suspension? And so this was my Prelude SH model, which has, the two lower ball joints, the virtual ball joints. And unfortunately, I'm not going to go through the FEA models. I'm going to have to show you videos and screenshots I already took, because I wasn't properly using configurations when I ran through this. I was just trying to get it done. And so everything kind of fell apart when things are hidden and unhidden and suppressed. So we're just gonna, you know, do it live, as they say. Okay, so, well, alright, so we've got the geometry. Well, what position should the geometry be in if we're gonna consider worst case? And here's the thing. So I said, alright, I think I actually did do the math here. Let's see. Oh, I just downloaded this. There we go. Okay, so. Right, so at 2.5 G's, the weight transfer is going to be high enough. Well, I said, what's the worst case condition? When is the inside tire basically going to fully unload? Now, that depends on a ton of things. A lot of things. But a simplified model can get you a pretty long way. So I made the assumption this thing needs to be stiff. And what do I mean by stiff? So if we're planning on hitting 2.5 G's, let's say 3 G's, we probably want to keep our body roll down to between 2 and 4 degrees. So let's say my max is 3 degrees of body roll, and I'm hitting 3 G's. That means my roll stiffness needs to be 1 degree per G. That means 1 degree of lateral acceleration gets me 1 degree of body roll. So at 3 G's, I get 3 degrees. Okay. And so then I went into my little model here and figured out what the vertical height of the tire needed to be. I'm not going to move anything because I can't remember if it's constrained. It's been a while since I worked on this. I think this was pretty far into last year. Oh, don't tell me my battery's going to die. I have been trying to record this video all night, and everything bad that can happen keeps happening, and I'm 3 hours into this 14-minute video. I need a phone charger. Okay, we're back. Where the heckaroonie was I? Alright, so I set the wheel and tire at the height it needs to be and probably gave it a degree or two of steer. Because you really don't need that much steering angle. And then I did this outboard knuckle reaction force. I just applied a unit load at the wheel and tire. And what I ended up getting was a percentage. Instead of putting the actual force in, regardless of what the force is, ignoring like bushing compliance and ignoring link bending and stuff like that, whatever force goes into that tire, these links, just because of the kinematics, the geometry, are going to have to react that force. So if we are looking here, there we go. Okay, so you've got your lateral link, which is this one. When I put a force into the tire patch, which is it's behind the wheels, it's behind the kingpin axis, and technically it's even further behind. You have pneumatic trail, which is in addition to mechanical trail because of the tire adhesion forces. But when we do put that lateral force in at that spot that I defined, due to mechanical and pneumatic trail, the lateral link takes up about 200% of the force. So if I put 100 newtons into the tire, this front lower control arm is going to have to react, what did I say, 100? So 201 newtons. And you're like, well, how can it have more force in it than put into the tire? Well, when you look at the side profile here, actually, let's just, that guy. If we're applying a force here, if we're applying a force down here, we've got basically reactions here and a reaction here. And so you can kind of look at this as like a wedge, where if I'm pushing on it, not a wedge, but I mean, it is a lever, right? So You know, when you crush a beer can or whatever, you've got you've got your kinematic advantage here, mechanical advantage. So if I put 100 in here, you know, the upper, if the upper was equidistant from the tire patch as the lower control arm, it would have to react force in the opposite direction. So it's going to push that way to prevent the tire from rotating, right? Okay, so now you've got 100 pushing this way, and you've got 100 pushing this way, and there's a pivot here. Oh, sorry. The top's not pushing; it's pulling. So this is pushing. The top is pulling, so that it doesn't rotate. So you've got a force going this way, and you've got in compression, and another force going this way, which is a tension force. But they're both going the same direction. So the load taken up by the lower control arm has to also counter the load that the upper does, just to keep the tire upright. And so that's how you get your 200% in compression on the tension link or lateral link. And look at this, the tension link, it only gets 7% of the load, not much. And then we look at the Fuka, 40% in its intention, and then we've got the tie rod, which is 70% in tension. And so essentially, if you're comparing these links here, your tie rod is a third of the forces is your lower control arm, and your tension link here is only 7%. Now that's lateral. 4F, so braking, accelerating, and potholes, your tension link's going to be taking up all the load, and your lateral link isn't really going to be taking up much, right? And so yeah, so I was able to use this calculator, or use those kinematic inputs to figure out the forces going into my links. Well, how did I get the tire patch force? This is where we do, I don't know what it's, shade tree engineering. Okay, so we make a guess about the center of gravity. I call it 400 millimeters. We know the track width, it's about 60. Curb weight, let's say it's about 3,000 pound at race weight. To load the safety factor into the design, we're going to say, hey, its a front weight distribution is 60%, which also means that any weight transfer, left or right, ignoring weight transfer balance, 60% of the transferred weight also has to go to the front axle, right? And we've got a front axle weight, rear axle weight, and if we're claiming a 2.5 max G, and the reason I went with 2.5 instead of 3 technically is I just wanted the force where the inside tire technically lifts, which gives you kind of a worst case. You could argue more or less, whatever. But if we're hitting 2.5 G's in lateral accel, then we've got to be getting some from aero. And so let's assume we have a really sticky tire. We're getting 1.2 G's mechanical grip. And the aero load distribution is 40% front, 60% rear. And so if we're hitting, there we go, if we're hitting 2.5 G's, which is this guy, and we subtract the mechanical grip of 1.2 mu or 1.2 G from that, and then we multiply it by the weight of the car, we figure out the normal load that has to be added to the car's weight on the tires to be able to produce a 2.5 G max lat. And so then we get front aero force, which is just the front distribution, and the rear, which is, you know, that number multiplied by 0.6, and then we come to front lateral load distribution. So let's say for an understeery car, we want to transfer 3% more load to the front axle than the rear axle. And so that would be indicative of understeer. You're going to saturate the front axle before the rear axle, which this is not mathematically correct, but it's ballpark correct. And that's all we really care about right now, ballpark correct, okay? So we're going to assume that 63% of the weight transfer in roll goes to the front outside tire, okay? And so when we calculate the weight transfer by saying, hey, we're going to hit 2.5 G's, and we're going to do that with 3,000 pounds, then that means the center of gravity, so your acceleration forces are going to act on mostly the mass center. It also acts on the unsprung mass, but again, we're keeping it simple here. And so you're going to have your forces from gravity acting on the center of gravity of the vehicle. And so that gives it a moment. The car wants to roll because a force is being applied 16 inches above ground. That is not 400 millimeters, is it? It might be. 400 millimeters divided by 25.4 is about 16 inches. Okay, all right. I'll believe the math. And what that means is we end up with a weight. Oh, okay, so you have that moment, but that moment has to be reacted by the tire. And so then you divide that moment by the track width. And that gives you the total weight distribution that happens in this 3,000 pound vehicle at 2.5 G's. And since we know how much total weight needs to be transferred, and we're making the assumption 63% of that weight goes to the front left tire, we now know how much weight goes to the front left tire, which means the front right is coming off the ground. So, like, there's other things to play with. But this gives us a scale. We're around 3,000 pounds on the front left at the tire patch. Okay, 26 minutes in. We've done 0 on actual cradle design. But I now know how much force is going into this link, which acts here. And I know how much force is going into the tie rod, which is going to have to be reacted by the tie rod mounting locations. And since this inside tire is in the air, we're going to assume the reaction is 0. That's fair enough. Other loads are under acceleration. Your transmission mount is going to take a brunt of the load. We're not concerned there. It should hold up just fine. Alright, so we've gone through how we're going to engineer this thing. So we know the package space. We're going to say, hey, we got to stay inside this, right? And we're not going to go outside of it. We're just going to stay right here. We know how much load's going into it. So we've got package space, we got load. But what's the target? That load is going to cause, well, the obvious target is the metal needs to not fail. It needs to not deform under primary loads, and it needs to not fail under fatigue loads. But stiffness still matters, so what's the target for stiffness? As a VD engineer, I just made the assumption that 1 millimeter of travel at this hard point is acceptable. I'm not going to claim that it's good, but for example, if you just had a bushing in here, you'd probably get 10 millimeters of displacement at max load. Or maybe 5, it really depends on the car. 5 is probably closer. And so we're going to bring it down to 1. I think 1 is a decent target for 3 Gs, which he won't be the entire time. So then we start designing, which means we can get rid of this. If Main Gear wants to sponsor me and send me a supercomputer instead of asking me every 3 to 6 months if I'd like to buy one, that'd be great. FYI, I'll take a pretty Main Gear PC. I would love that so much. Okay, so this is where we're starting. I was going to run just a baseline FEA on this, but here's the problem. To do FEA, I need a solid model, and I just have a bunch of pieces stuck together here. Alright, so now we have to redesign the original model. Now, I made the assumption here that oh yeah, this is going to have so many errors, because I did a lot of FEA and stuff after I designed it, and then went back and made changes, and then once I got the main structure good and verified everything, I then went back and added sway bar bracket mounts, and so everything's messed up, which is why you're not going to see any of this FEA stuff. So I made the assumption that the fabricator would chose some of this design for some reasons. I assume that this is going to be plates that are cut. That's a plate. Tubing's pretty obvious. I thought that maybe because of the geometry that these pockets were going to be billet pieces that were welded to. And what I did is then matched the same design to the real geometry of the car. And so these are the actual Honda OEM hardpoints with no ambiguity, just straight up from Honda. And I made it one solid piece, right? And so we can go ahead and get rid of this guy now because we're over it. And hey, we've got this. This is reasonable. We can do FEA. Where'd we end up? I don't remember, but I know that I got videos on it somewhere. Sort by date. And we're going to go back just a little bit. Here we go. Alright. So, there it is. Alright. We are looking at... So, this is the red is the yield strength, which means anything that lights up red is going to experience permanent deformation and or failure on one cycle of that load. So this Cradle would basically tear itself apart as soon as he went around one corner at 2.5 Gs. Not ideal. And the displacement, I think, was 6 millimeters. So his front lower control arm inner point would displace 6 millimeters just from structural stiffness, not including bushing deflection or anything else. So not great for alignment. And so I sent these results to him with the displacement and the stress and fatigue, and he said, hey, can I just like pay you more money to redesign it? And I was like, absolutely. If I only need to provide electrons and the R&D and development part is done, that's what I'm good at. The whole finishing and manufacturing on a non-existent budget really causes some issues. I think, yeah, this other video is just a comparison of essentially what I just walked you guys through. Yeah. And so, then we get into my design. Yeah, we'll start here with a few things. So I'll show you where I ended up, and then we'll talk about how and why I got there. So that's the mesh. What is this, V3 with welds? Hell yeah, brother, let's go. I know, everything's wrong. Okay, we're alive. So, you can kind of see I did things a little differently than they did. Just a wee. I put material where the load paths actually are. And these had to move and be bent to clear the steering rack. So, understanding packaging space, like really understand packaging space, was step one. We're going to go ahead and press that bad boy. Yup. Alright, we're just going to hide this for now. Okay, so, as mentioned before, we went ahead and did some in-house 3D scanning with something we already had in-house. Now this gives us the Cradle packaging space, but there's a lot of missing parts. So I had to reverse engineer the steering rack. Alright, we got a freaking steering rack, my guy. Insane. I'm gonna go ahead and open this up and make it easier to look at. I said easier to look at. Alright. Come on, give me something here. That's better. Okay, so I did 3D scan it, which, you know, shows up right there. And so there's a couple things here. I made sure to align this shaft with the valve body. I made sure to align the bolt holes here. And then, what else did we match up? Yep, we got the boot. We got full extension. Do I only have one config for this? Yes, I do. Okay. And then this is the max articulation in space of the tie rod. Now, caveat to this is what the tie rod can do. This is not necessarily what it will do attached to the suspension. But for installation removal, I said screw it, we'll cover this. And so I made sure that everything kind of lined up pretty well. You know, everything looks like it lines up pretty well everywhere, you know. And so I scanned the rack on its own, but I also scanned it in the cradle. And the reason I did that is so that I wanted the CAD to match up to the 3D scan, but I also wanted the position to match up to the real thing. So I made sure that I overlaid these two 3D scans, and all those same important points lined up the best that they could. And this essentially ensured that the rack was in the right place. And what we ended up seeing from this guy is, look at that. The tie rod boot interferes with this, which presumably is why the OEM made it curved. So when I saw that this was curved instead of straight, I was like, oh, well, they did that for a reason, just like they do everything. And so that I found that curving it was absolutely necessary. So that was a lot of work to get all this stuff to line up. What else did we throw in here? Steering rack bushing. It's not super important. Okay. So to ensure that my 3D scans are accurate so that my CAD can be accurate, we do what I like to call check fixtures. And I'm going to unsuppress both of these at the same time. There we go. And we are going to go ahead and show that guy. And I have no idea why we don't need this anymore. So let's get rid of that. Okay. So what I do is I design these and then I 3D print them. So to ensure, because what's important is that this pinion location compared to the main mounting bolts is perfect, right? And so, and I also wanted to ensure that the surface of this mounting point is correctly axial, or its orientation is lined up with the axis of the shaft. And so these are three different components that I lined up, and what I was looking for is this snaps onto here. Yeah, so this snaps onto here, and when this piece and its little pokey guys come through the bolt holes, so this kind of just sits in these bolt holes, that when this is snapped on, these guys perfectly line up to the center of these guys. And why did I not make them an exact fit? Because if there was any unalignment, I wouldn't be able to measure what the misfit was. So if they're all offset by 1/2 mil to 1 mil in any direction, I know which direction I have to move and exactly by how much. I can measure that. And just like if the points between these bushing holes were different, it would show up in this. And so once I knew this and this guy were aligned to each other, I then printed out this guy, which sits exactly on the pinion in an exact position that lines up on here. And ideally, when we mate these two, what happened? Oh, my mouse got turned around. That happens. And so ideally, when this is sitting in the right position and this is sitting in the right position, that these legs here end up perfectly centered in here. And that these edges should line up with these edges, and these should be equidistant from those. And so when I printed these and put them on the steering rack, I was able to see exactly within a couple tenths of a mil where I was off. And so that was my fixture jig for the steering rack. And I also did well, let's just see what these are. Okay, so this guy and that guy are the OEM clamps for the steering rack and the steering rack bushings. We'll go and hide those, we don't need them. Alright, so for jigs, we have the top bolt pattern. Okay. And let's go this one. Okay. So this jig, we have the main transmission mount is these 3 points, and then we had a couple fixtures. For different accessories, and so I 3D printed these and checked their alignment. I actually think there's a picture in here. No. Well, I can pull up the picture somewhere, but you get the idea. And so when I put the bolts in, these little nubs would make sure that they're aligned perfectly, and then I can use it to check that all these bolt holes line up exactly where they're supposed to. And then these obviously are for those guys back there, which is not a feature he wanted me to add. So then we bring it back open, and so you can see that everything just kind of lines up. So that was for that pattern. And then to ensure that the measurements were correct from the hard point to the body side points, I made this jig out of all these different pieces. So this locks into this and gives us an exact reference point between not only these two planes but the center points. And because this locks in perfectly, it clears the cradle. I was able to attach it to these pieces, which also lock in the very center point of the front lower control arm. It gave me an exact offset to measure from this cradle point, and then it also tied in the stay bar mounting points here. And then with the manufacturing tolerances, you're going to get issues. And so I have to take it upon myself to say, okay, here's what the 3D scan's telling me. Here's what real world physical measurements are telling me. What do I think the engineer was actually achieving? Is it supposed to be 69.9 millimeters, or is it supposed to be 70? Pretty good chance it's supposed to be 70, but if your measurement is something that's unrelated or not geometric, it could very well be 69.9. And so that's where the error in reverse engineering comes from. Um, if you ever wanted to look into culture and the concept of it, essentially the idea is people assume that other people know what they're doing, and so they will repeat them, except expecting to get the same results. And what that ended up being is when the English were running around island jumping during, I don't know if it was, maybe it was World War II or something. Uh, they came into an island, hung out with islanders. Islanders saw that planes flew in, provided food supplies, left, and then the people left. And the Brits were helping the people on the island, and they became a little dependent. And then when the Brits left, they were still an airfield. And I want to say something like years later, someone came by and saw that they had like built fake planes and like all the fake stuff you'd need to run like a small terrain based airport, and they were trying to do the motions, and planes just weren't landing and giving them supplies. So it's kind of cargo culture, and it's very relevant for many reasons. But with reverse engineering, it's really hard to know exactly what the engineer was knowing. You have to use experience and knowledge and good tools, because this kind of stuff isn't going to be super accurate every time, which is where some of the tolerances come from. Side note, I keep seeing people talking about building spacers to put on in your car body to center the cradle, but the bolt holes are that big and the body holes are that big, not because of just manufacturing tolerances. So the assumption is when you machine the spacers and you put them in, it makes the hole smaller and locks everything else in tighter. But your cradle's not straight and your body's not straight because of manufacturing variance. So when you put the car on the alignment rack, or when they build them in the plant, because they have pins that pin in all the locations. So like from the assembly plant, it is imperfect parts are assembled and mated together perfectly. And so what that means is you put your car in an alignment rack, you get the toe and camber dialed, and they're perfectly symmetrical. You're like, yay, my car's great. Then you go drive it, but it behaves differently left to right. Why is that? My alignment's perfect. I don't know. Well, it's because your kinematics aren't perfect. You can adjust your alignment to whatever for the most part, right? What happens is if your cradle's twisted in the car in whichever way, your kinematics are going to be slightly different left to right. So the proper way to align your cradle to the car is to not use these spacers to force it into a locked position. What you want to do is put it on an alignment rack, and you want to lift the body up and lower the body down with weight or whatever, and watch the camber and toe curves change. And you want them to change evenly. And so if you have more camber on one side than the other, like a more aggressive curve, that probably means your lower control arm is further out than it should be, which is going to cause a more aggressive curve to one side, which means you need to move your cradle a little bit this way. And you can deduce all the directionality based off the numbers and stuff you get. And then you use a torque wrench and you torque it down. Like, that's what you're supposed to do. Anyways, okay, so there's that jig, there's all these jigs. Okay, so what do we know? We know the force that needs to go in. We have a target for the performance is don't break and deflect 1 mil at the lower control arm. And we have our packaging space that's fully confirmed. Now that we're 52 minutes in, we can get into the design. So I'm just going to jump over to here where it's a little easier. Alright, so obviously I'm not going to show you everything here. But I can kind of walk you through it. So you've seen the... Oh, that's not in here. Well, I think you've seen the 3D scan enough. And so I did a couple iterations of this. And if we want to walk through a few of those, if we can, what do we got here? So this is, I think, the same one we looked at. Maybe a little different. Maybe not. Interesting. The rest of these might have been screenshots. Where the heckaroonie did my file go? I guess I won't show you the earlier versions just yet. Or maybe not at all. So what I originally did was I just started with these tubes. I said, hey, let's get these tubes as far out of the load path as possible, or from the neutral axis as possible. So 2 tubes here, and then a bridge here for stability, and then, you know, 2 tubes here. This actually ended up being kind of a pain. But luckily, something to take into account is if you're constraining your model by these points, you're assuming the chassis is infinitely stiff, which it isn't. This is a chassis stiffener, okay? So you have to take that with a grain of salt. And so yeah, I started with these main tubes here and said, okay, where does this get us? And the results were subpar. I think when we looked at the deflection of the original one, it was like 6 millimeters. I'm gonna have to blur so much of this out, but there's us walking through it, going over it. This is me talking through some of the choices I made. Here's some of the results from that original one, just as an overview. This is fatigue. So this is running multiple hits in anything red would have been considered a failure. This is stiffness. So yeah, you can. This is exaggerated load by, I want to say, maybe 5x. Yeah. So that's still a lot of deflection, right? Yeah, we're looking at 4.5 mils. Okay, so maybe it was 4.5 mils at 2.5 G, and I think 3G got it up to 6. Yep, that was still the original design, and then I think this was the first iteration where I basically walked him through everything I just walked you guys through. Yeah, where are we at here? So okay, so this is the original structure showing fatigue analysis, strain, and then so here's mine. This is how the cradles compare, basically side to side here. Yeah. So there was that little hotspot. I think that is what that was, actually. I don't know where the heck the videos went, but I guess I can. Okay, so what this is it is a bit exaggerated. Essentially, anything that's red could be limit the plastic strength limit of the material. So anything above red that was something I ended up will deform. This is at 3Gs. 3Gs, okay. And anything that's not blue may deform over repeated uses. And so there are some hot spots here that I need to clean up. That shouldn't be too difficult. That was okay. So that's another aspect I missed here is when you do the FEA, what stress and strains to use. So SolidWorks has pretty decent standard materials. Let's see, we used 4140 or 4130, my bad. And it's got its own stress, strain, and temperature? I don't want temperature. I don't know where the fatigue curves are. But this is assuming a strength of 5,600 newtons per millimeter in tensile, but it yields at 4,600. That's a pretty high strength material if you're using 4,600. A typical like OEM structure would probably be, you know, in the 350 to 450 range. But that's yield. We don't want this thing to yield. We don't want it to get close to yielding. We want it to be just under yielding. But that's for one cycle, not a ton of cycles. And so you can go down this rabbit hole into mechanics of materials and everything.
and how welds affect properties and all that. And what you kind of end up at is you end up with a fatigue limit about 30 to 40% of the um, yield strength. And so I see a lot of people doing FEA, and they're like, yeah, I put the material in from the table and I hit go and it wasn't red, so we're good. Ignoring stiffness completely. Um, but fatigue is so important, and as soon as you weld any of this stuff, it gets so much worse. And so for those videos, or that video that I showed here, what I essentially do is I set my limit for my color. Um, Everything below the fatigue stress just stays blue, and then anything between the fatigue stress up to, I think, 75 or 80% of the yield stress um, is in the color scale, and then anything 80% above is red, and red needs to be addressed. Um, and so that's where all this extra bracing came in. Was this bracing, especially up here, that's missing a weld here, allowed me to get rid of all the red hot spots. I tried making this thinner. It really didn't work. This really ties in a lot of this. Um, the steering rack technically does provide some stiffness. In the OEM Cradle, actually has quite a bit of bracing down there. Oh, there we go. So, oh, I don't have it here in the scan. My bad. There are panels that tie in to, so like little S-shaped guys that tie in this point, these points, and this point, and again here, 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 and here. And that box is in the steering rack. People like throwing solid steering rack bushings in steering racks so they perform better, but here's the deal: your steering rack isn't meant to be a load member, and the more load you put into the steering rack, the more likely it is to deflect. And if you have hard bushings in your rack itself is going to deflect instead of the whole assembly deflecting in the car. And what you're going to do is you're going to wear your steering rack out a lot more, and you could run the risk of binding your steering rack. So you don't want to use your steering rack as a structural member. You want your structure to be as stiff around the rack as possible. Um, yeah. So these braces really help tie in the fatigue issues here. I did my best to take weight out, and if I remember right, we ended up maybe a pound heavier. Let's see. Oh, stiffness analysis. What was this one? Let's see. Wait. Okay, so OEM was 28.6 pounds. Cory's first iteration was 24.3, and mine ended up being 30.2. I want to say I got a couple pounds out of it later. Yeah. How much does this one weigh? Let's see. Let's see. Oh, 33 pounds. Okay, so it did end up a cup, 3.5 pounds heavier. I'm pretty sure. Oh yeah, because then I added in the stay bar brackets. Um, all right, so that's the engineering that goes into the design. But what about the actual design? I don't like wasting time, so I like my CAD to be extremely structured. So we're just not going to save anything, and we're just going to play around here. So if I want to change anything early on and have it populate back out, we need to define some things. So we define the cradle hard points. We've got all the hard points right here. We've got our steering rack center line, the lower control arm hard points. We define a couple planes. And then we made our cups. So I think these are actually going to be a few pounds are going to be pulled out of these. I think 1 pound actually, because he's going to just weld a washer in instead of having these machined. For me, it would be less labor to machine these versus cutting out everything and welding it. So we can just start one at a time here and run through it. So we've got nothing, and now we've got 4 of these somethings, and we need to define the proper geometry for the clevis. So this is your hardpoint center lines, and then kind of the angle they have between each other. That actually was difficult to verify. And so now we have planes that these sit in, center planes for those hard points. Those are the clevis planes. And now we start actually building. Again, I wanted to maintain what I thought the original fabricator was going to do, because this was for them, not me. And so this is basically assembled through send, cut, send. And yeah, oh, there we go. We mirrored the side flange, and now we mirror the entire clevis, so that any change we make over here auto-populates to everything else. And then we've got to add the plane for the transmission mount, which is right there. And we throw the bolt holes in because we have the jig already. Go ahead and hide that. We've got the flat plane for the mount and the threaded bolt bosses they go into. I guess, oh, this is the fun part. And then we get into the skeleton. So I don't want to make individual tubes, because if I have to change anything, then I have to change everything. And I don't want to change everything. I want to change one thing and have everything self-populate. So I decided it'd be way easier to not show you the actual drawing, because the dimensions were taking way too much effort to hide. So I'm just going to run back through this real quick. There we go. Tube structure schematics. Right. Okay. So, yeah, like I said, I want to be able to just change anything in the beginning and have it self-populate, so everything has to build off the previous structure. So I didn't start by building this entire drawing from scratch. I started with one tube and then another tube, and so I would draw the pathway for the tube, and then I would create it, and then I would draw a pathway, go back into this drawing, and then create the path for the next tube. So it's not like I did this, it was still iterative, but I always came back to this as the base drawing. And so the way I do that is we've got an ID and an OD for the tube defined here, and then I've got a reference dimension so that this line always equals the ID, and then these two little lines top and bottom represent the thickness. And so you can kind of see the construction lines that I use to define certain relationships. This is to keep things very consistent. And so I just draw the path in a 3D sketch for where each tube's going to go. And then when I actually go to make the tube, all I do is literally copy the drawing from before for the profile, and then I copy that line from the 3D. So these are actually just not dimensioned at all. I can show you these, right? So there's nothing here. This is literally just a copy of a drawing. So this is, I don't know, a ghost sketch, an artifact sketch. I don't know what you want to call it. And then same thing with this one, right? There's no dimensions. There's nothing's called out, but it is fully defined because again, it's pulled from this one. And so I end up going through that, you know, with all these other tubes. And so, for example, here, I wanted this tube on this edge, and so I needed the OD to be able to place the center of this tube location, right? And so we've got the ID, this brings it out to the OD. We make this line perpendicular to this line so that it actually projects onto the surface instead of saying, because if it's at a 45-degree angle and it's an inch wide, it'll project a 1.41 inch profile of like an ovular profile, and that's not what we want. Well, on the surface it will project an ovular 1.4 inch profile, but we don't want to define the pattern on the surface to have that projection. Man, I don't know how to explain that the right way. So if we reference this edge to this circle, and we have that pushing at an angle, and you say, hey, I've got this circle on this surface and I want it coincident with this point and this point in space, it ends up messing up the geometry. Actually, it'll end up looking like a squished oval if you do it that way. And so this allows me to properly project the intersection of the tube, which is really what we want, is the intersection of the tube profile. And so there's only one dimension called out for every unique dimension in the entire assembly. So this ID and OD that I call out in this tube, I will use it everywhere. Like I showed you, I used it there. I'm using it over here. Let's see, where else did I use it in this drawing? I don't know, but you get the idea. This is just a curved radius. It's not actually a spline or anything, and so you can just use a curved mandrel bent curve and weld that in. But yeah, so these are really robust drawings. There's another example of where I use it. And then every further drawing from here on out just uses those. And yeah, this drawing got modified I don't know how many times going through the iteration of everything, but it's nice because if I wanted to just change the thickness, the diameter, any of these radii, I change it in here and I hit go and it rebuilds the entire assembly without issues. Sweep the tube, and so this auto builds everywhere. And so what do? We just plug and chug and do the rest. Cleanup, that's a fun one. Is there anything defined in here? Nope. So this cleanup is simply the profile of this guy. And it is deleting all the material from this so that you get your exact shape of your tube that intersects. So no other CAD needs to be done to clean that geometry up for the final product. And we just keep going through. Some more cleanup. What do we got here? We've got clevis to brace plane. And then we add that guy in. So that plane is just normal to the profile of that guy. I'm going to guess we clean it up, mirror it to the other side. Uh-oh. Yeah, we just keep doing the same thing. And we just keep adding, like none of these drawings require anything. because they're self-populated from this original drawing. And then I decided later to add all the accessories because I also needed extra stiffness. And then we do a little weight reduction. And we put the attachments in. And I think that just cleaned up that edge. That's all that was. Main bar cross brace. We add that back there. Oh, we're starting to throw welds in now. We're welding. Front weld, rear weld. Clean up the weld. Steering rack bosses, so these need to be threaded. And then we clean up the bosses. Front brace plane. Cradle force vectors. So this is where I start putting in the lines to do the FEA. Since I won't be making this, we're gonna make. Uh-oh. What in tarnation happened there? I don't know. But anyways, we got the Bibs logo. And we throw the braces in. What's next? Support bar, clevis, and plate cleanup. That guy, there we go. So that's just literally putting a flat plate in, and then for the cat I trimmed it out. This will get laser cut and welded in. And then we throw it onto the other side. Next, we've got this main plate with just some little bends at the end that can be done by hand or on a bench. And then we take a little weight out. So, let's see, out of all of this that I've done so far, from the tube schematics all the way up to this guy. Nope. Wherever this one is. Yeah, wherever we added that in. So I did 20-25 features before I had to actually dimension or draw anything, because I based it all off this original tube schematic here. Oh boy, there's a lot here. This is a long video. I apologize. I mean, you get the idea, right? So we just keep adding stuff. I think I need to rebuild here. Oh, yeah, we're doing geometry for the plates. We've added some more plates in. Stay bar bracket profile. Let's see, does that have a drawing that looks interesting? Not really. It's pretty straightforward, pretty simple. Let's see. Cleaning up the stay bar bracket. So these is basically two stamped pieces, stamped and bent pieces. Clean that up. Throw in the bolt bosses. And we're like, hey, we're done. So when we're here, we've got a bajillion individual pieces. See? So that way I can export this step file and I can extract every single individual component and figure out what has to be machined and what has to be done through send cut send, right? And then it's because I can't fillet, so I can't add a fillet to any of this. Now, proper design would say you don't do fillets, you draw in the shape of your weld. But nobody's got time for that, and I'm not doing the welding. So we do a combine, and then I can just start adding fillets everywhere. So yeah, now we've got fillets, we've got welds. Gets rid of the hot spots when doing the FEA. The FLCA center sleeve here is simply just for doing the FEA, so there's a reaction to this. You're assuming a bolted connection. What else do we got in here? Okay. Well, yeah, that's basically it. So like in all of this, there really isn't a lot of drawing. You know, I had to make these clevises, which, you know, it's literally just a single drawing with a rotation, right? Oh, I guess I don't need to. I can avoid showing. There we go. It's a single drawing, and it's just rotated. And then same thing here. This is just a single profile, right? This, you know, there's a lot of work into this drawing, even though you can't really tell, because it looks kind of simple and kind of elegant. So, yeah, I have a bajillion shortcuts on how to do drawing constraints and stuff like that, which is not going to be for this video. This video is just general design. And so what I ended up with is something that I'm confident will be stiff enough for a race car that wants to push 3Gs. You know, it gained 3.5 pounds over OEM, but it's significantly, well, actually, to be fair, I don't actually know if this is stiffer than the OEM. I suspect it's similar. I really would like to do a full analysis of the OEM one, but then I would literally be reverse engineering the entire, like every stamping from that, and then trying to do FEA on this laptop, which would probably take forever. But honestly, I'm maybe it is, maybe it isn't. Will an OEM Cradle deflect less than 1 millimeter at 3Gs? I want to say it wouldn't, because it was never designed to, but I know this one won't, so I don't know. I have confidence in its performance. I don't have really a baseline comparison, but I know its fatigue strength is significant, so it's, you know, it's not going to fall apart. And you know what, if you hit something or hit a pothole, your fancy Cradle is not going to get destroyed. So yeah, I don't know. I haven't really done a video like this before. I know I should have been doing, because I have a ton of these projects. I just don't have time to do this, and I'm not going to do a ton of editing because I just don't have time. So you're not going to get any fancy, crazy, fun, planned out videos, because if I plan out a video, I'll spend 3 weeks planning it, not working on anything else, and something will come up, and then I'll have to go work on that, and then I'll forget what I did and say I'll get to it later and never get to it. So if you guys want to see stuff, ask for specific things and I'll go through it. If there's anything you want to figure out how to design, if you need tips and tricks on how to make your drawings robust so you can do all this work, change one thing in the beginning and everything populates without it crashing out. But yeah, I want to put more content up on YouTube. I want to help people get better at making things. I want to help people make things. I just want to make things, man. Or mammet. Or men? May? I don't know. Anyway.